True or false? According to the kinetic theory of matter, all molecules are continually in motion. One of those answers is correct. Kinetic theory of matter. What's the word kinetic mean? Moving. Okay. So according to the kinetic theory of matter, all molecules are constantly in motion. That's true. Are solids then in motion? Do they appear to be in motion? Okay. At what level is the motion taking place? At the atomic or molecular level, right? That's why we look at something that's solid and it appears to be stationary. So why does it appear to be stationary? Other than the fact that we can't see down at that level, why isn't everything always physically moving? Yes, ma'am. That's more accurately it, right? That there's motion taking place, like I used this marker yesterday as an example. The molecules in this solid marker, this isn't liquid or gas, right? This is solid. We agree on that phase? Okay, but the reason why it doesn't appear that this solid object is moving or other solid objects are moving is because at the molecular or atomic level, all the motions have countering motions taking place and they offset each other. So while one molecular atom might be going to, let's say, toward this direction, at the same moment there's other motions taking to this direction and they offset each other, and so the net is no motion to the total solid. That's what the kinetic theory of matter says about solids. What about liquids? And my hand motions apparently become popular, so they're learning them now in the middle school, so by the time they get to here and I go, now solids, and they'll go, solids. So they're learning it this way, that solids are, the molecules or atoms are in relationship to one another, and they're vibrating back and forth. That contradictory motion, or the offsetting motion, is taking place as they vibrate back and forth. When we go to liquids, the motion looks something more like this. They still are relatively close to each other, so I keep my hands in contact, and they're moving like this, but they're not fixed in place relative to one another. In other words, when they're solids, they're kind of stuck together and vibrating. But when they're liquids, they're not stuck in relative position to one another, but they're moving around. And this is in contrast to gases where I take my hands and I move them apart. If you remember, I drew on the board yesterday. You can have a solid, think of it an ice cube. Those water molecules in ice are moving, but they're just vibrating next to each other. When it melts and becomes liquid water, we have it in our hands and it runs through our fingers. Those are molecules that are in proximity to one another, but they're not fixed in place relative to one another, and they're moving around. And we're going to see in the lab when we do them that we take a beaker. We're going to actually modify the lab a little bit. We're going to take 3 different beakers. In one of those beakers, we're going to place ice water. In the other one, we're going to put room temperature water. And in the third one, we're going to put just sub-boiling water and put food coloring, a couple drops of food coloring in each one of them. Now, based upon what we've talked about, the kinetic theory of matter, what would you expect to happen? What would be your hypothesis right now on what you would expect to see in those 3 different beakers of water? Let's talk about the cold water first, relative to the lukewarm and then the hot water. What would you expect to happen when you drop that food coloring in there? Just think about it for a minute. We haven't really talked about this directly. Are the water molecules in all 3 beakers in motion? Yes, they're in motion. Remember, I drew on the board, I drew an outline of a beaker, and the molecules are bouncing off the walls and bouncing into each other, and they're all moving in that space. Even though the water isn't, you're looking at it, it's not like sloshing back and forth, but the individual molecules are moving. That's what the theory says. And if that's true, when the water is cold, and we put a couple drops of food coloring in, what would you expect to happen to the food coloring? What we're going to see is the food coloring is going to drop to the bottom. Now, why would it drop to the bottom? Assuming that the coloring is more dense than the water, correct? So it would drop to the bottom because the higher density goes to the bottom, the lower density comes to the top. So it would drop to the bottom, and something's going to happen to the food coloring. In all 3 cases, what do you expect is going to happen to the food coloring? If there's motion taking place, it would disperse. Eventually, all of the water will become green. Let's say we use green food coloring. All the water would become green without you touching it, if the molecules are actually moving in there. Because while you put the food coloring in there, as a matter of fact, I was talking to my wife this morning. I said, hey, do we have any food coloring? I can't find the food coloring. She says, John, they don't make food coloring the way we're used to where it just drops like ink. They've gone to kind of these gels. I said, food coloring gel? She goes, yeah, you can take the food coloring gel, put it in the beaker, and stir it up. I go, that defeats the purpose of the experiment. The purpose of the experiment is if I have water that appears to be sitting stable and still, and I put a drop of food coloring in it, and it drops to the bottom, if water molecules stayed stationary, then you would expect nothing else to happen. But if water molecules are moving around, you would expect them to eventually bump into the food coloring, and that motion of the molecules bumping into the food coloring will distribute the food coloring equally throughout the beaker, right? The same effect as stirring it, but rather than us using a spoon or a stick or something to physically stir it, the molecules of water themselves will do the stirring as they move around inside the beaker. So I'll tell you right now that we would expect in all three beakers, with ice water, room temperature water, and just sub-boiling water, that in all three cases, the water will take on the color of the food coloring. The water will self-stir the food coloring and distribute it within itself. But, based upon the kinetic theory of matter, what differences would you expect to find between those three different beakers? Correct. The rate at which the mixing takes place. Again, according to the kinetic theory of matter, energy is needed, and energy is used whenever the molecules are moving. It takes energy to do that. And molecules get their energy from their surroundings. Now, in this case, when we have cold water, lukewarm water, and hot water, we've got three different energy levels. Which beaker has the highest amount of energy? The cold, luke, or hot? Hot has more energy. Has more energy in the system. So because the hot has more energy, what would we expect the molecules in the hot to be moving? Faster or slower? They would be moving faster. Lukewarm would be moving at kind of a mid-velocity, and just above freezing would be moving at a slow velocity. If you think about it, if we were exactly at 212 degrees Fahrenheit or 100 degrees Celsius on the hot, we would have molecules that are moving as fast as they can move before they break free of each other and become gas. They're still liquid, but they're right at the border of becoming gas. And so they're moving as fast as they can and still be in that phase. And if we think about the cold water, if it's at 32 degrees Fahrenheit or 0 degrees Celsius, the water in the beaker is at that point where if it goes any cooler, it's becoming solid. It can't get any slower without forming connections with other molecules and just vibrating. So we've got the two extremes at 100 degrees and at 0 degrees of the amount of motion we can expect, with room temperature being somewhere in the middle. So what we'd expect to happen then is the hot water, the molecules are moving faster, and because the molecules are moving faster, the food coloring will distribute quicker. On the low end, the just barely not freezing water, you would expect the molecules to be moving slowly, which means it's going to take longer for the same mixing action to take place. And again, room temperature being somewhere in the middle, closer to the hot than the cold, because of the temperature difference. Let me correct that. Closer to the cold than the hot, right? It's closer to freezing than it is boiling in this room right now. So some of you might disagree. Some of you think it's freezing in here. Some of you think it's boiling in here, but it's really closer to freezing than boiling. Okay? But in any case, that room temperature water is going to be somewhere in the middle. It's going to mix to a certain, let's say we put the same amount of water and the same amount of coloring, they're all going to eventually be the same shade of color. It's just how long does it take it to get to that shade? Any questions on that? On the application of the theory of, or the kinetic theory of matter? Remember that solids become liquids at what's known as the melting point, and liquids become gases at the boiling point. Also remember the unique things about those 2 points. I know we've covered this before, but what temperature is ice water? When is it not 32 Fahrenheit or 0 degrees Celsius? You can modify the pressures, but at standard pressure, ice water is always 32 degrees Celsius. Remember, if it's greater than 32 degrees Fahrenheit, 0 degrees Celsius. Let me just go to Celsius, 0 degrees, okay? If it's any warmer than 0 degrees, if the whole mixing temperature, if the stable temperature was greater than 32 degrees, it would all be liquid. If it was all less than 32 degrees, it would all be solid. When it's got both phases together, when you've got ice in water, you've got solid in liquid for water, that is at 0 degrees Celsius. And so as long as you have ice water, you have 32 degrees Celsius. Correction. Let's get Fahrenheit and Celsius straight. As long as you have ice water, you have 0 degrees Celsius, 32 degrees Fahrenheit. Ice water. If there's any water in it, it's not all ice, and it's not colder than 0 degrees. And if there's any ice in it, it's not warmer than 32 degrees Fahrenheit or 0 degrees Celsius. Okay? So when you have both phases together and the temperature is stabilized, you have 0 degrees Celsius. On the other side, if you have water that is boiling, how hot is it? It's going to be 100 degrees Celsius. If it was any cooler than 100 degrees Celsius at standard pressure, right? If it was any cooler than 100 degrees Celsius, it would not be boiling. And if it was hotter than 100 degrees Celsius, it would all be gas. So in order for it to be boiling liquid, boiling water, it has to be at 100 degrees Celsius at standard pressure, at 1 atmospheric pressure. Now that's why, remember before, why we've got different baking directions and different cooking directions for people that live at high altitudes. Because at high altitudes, it actually boils at a lower temperature because there's a lower pressure. So you ever notice on the back of those boxes and recipes, you'll see a high altitude cooking directions. They're different. Usually a recipe says, take this pouch, for those of you that don't work from scratch anymore, I don't know how many people really do all the time, but you have a pouch that says, put it in boiling water for 10 minutes. Well, you can say, well, what temperature is the boiling water? Duh. That's the commonality from everyone. It's not like, okay, put it in the oven at, was it 375 or 400 or 350? Well, it says 350, but my oven is cold, so I set it for 375. You're always trying to figure out what the temperature should be. If it says boiling water, it's going to be 212 degrees Fahrenheit or 100 degrees Celsius. It's going to be that. And if it says put it in an ice bath, ever see recipes that say that? Put it in an ice bath. Why? Because you're putting it into a medium that they know is going to be 0 degrees Celsius or 32 degrees Fahrenheit. It's a standard. And so because they know exactly what temperature you're going to have, they know exactly how long you need to leave it there. You get very precise cooking by using boiling water or ice bath water because you know the temperature. You're not questioning what it is. If it's all solid, it could actually be colder than 32. It could be, 0 degrees Fahrenheit, but it's still solid. Or the water could be at 300 degrees Fahrenheit, but it's all gas. And it could be raising and lowering. But when it's in those phase transitions, you can know exactly what the temperature is. All right? Feel comfortable with that concept or those concepts? Remember, lack of feedback is, yes, I understand completely, let's move on, right? So that is your nonverbal this morning, other than it's warm in here or I am really tired. Those are the other nonverbals that I'm getting, but you know what? Started a new routine, my new Year's routine. I'm getting up at 5:30 every morning, no matter what I have that day. So if I get up at 5:30 every day, my body gets into 5:30 every day. So I've already been up for 3 hours. Already spent an hour 15 studying chemistry today. How about you? No? Oh, man. All right. Yesterday I made a joke about density. Nobody chuckled at all. I'm sorry. Really bad adult dad humor kind of jokes I use in here because that's who I am. I'm a slightly past middle age dad. And so if you relate to your dad, you're like, oh, Dad, he's so corny. That's me. Okay? Because yesterday when I wrote on the board and I drew this diagram, which every time, or I drew a figure on the board, and every time I draw that figure, people giggle. So I'm not going to draw it right now, okay? Especially back there. But the 3 different densities, and I said, the most dense thing falls to the bottom. That's where the F's live, right? Because they're the densest, right? So the F's go to the bottom, the C's go to the middle, and the A's, who are the least dense, rise to the surface. So cream rises to the top. A's are on the top. Least dense is on the top. If that helps you remember, the densest things go to the bottom. Hey, trying to understand the concept. But this idea of density, remember, we did cover this before. We've done it actually twice before because it fits in this edition, in third edition at this point. Density, the definition here, let me just read it, is an object's mass divided by the volume that the object occupies. Density, the Greek symbol rho, is mass divided by volume. Go ahead and write that out. Mass divided by volume. So let's think about this. Chemistry is the study of everything that has matter, right, and takes up volume. Matter is mass, volume. So chemistry is really about densities as well. Matter, volume. At this point, hopefully you would accept that right now the way we understand matter is that all matter is made up of some subatomic particles that are common to every. We talk about all the different elements and all the different molecules that can be made from all those elements, but every one of those elements is made up of some basic particles. We haven't covered all of them, but for the context of this class, what are the basic subatomic particles that make up everything that has matter? Right, neutrons, protons, and electrons. So far, the basic building blocks of every atom are those. So protons, neutrons, electrons come together to form atoms that come together to form molecules, which is the basis of everything that is in terms of chemistry, those things that have mass and take up volume. So, if I have a certain quantity, and let's just say a snowball's worth. I know you don't have a lot of experience of that here in the Mid-South, but up in Buffalo, like everything is related to snow this time of year, right? So if I had a snowball's worth, whatever that may be, a snowball's worth, if I have a snowball's worth, that's a volume, isn't it? Look at, I keep my hands together. There's a certain amount that I can hold. That's a volume. If I have a particular volume, and let's say that my hands, a snowball's worth of air. Okay? I've got that much air. And let's say I were to replace it, that same volume of air, with lead. Which would be heavier? A handful of snowballs worth of air or a snowball's worth of lead? You agree with me that the lead would be heavier? So if I had, Star Trek, I had somebody beam out the air and then beam in the lead, suddenly, whoa, something changed. What changed? Remember that weight, the heavy, is the effect of gravity on matter. I could then say, this is heavier. What does that mean? That means I have more matter in my hands than I had before, right? I've got more matter. It's heavier. I've got more, think of it this way, I have more protons, electrons, and neutrons in my hand when I'm holding a handful of lead than I do when I'm holding a handful of air. Agree? But I have the same volume. It's taking up the same space, but one has more stuff packed into it. What appears to us to be heavier has more stuff for the same amount of space. That's the idea of density. But when you talk about density, you're talking about how much stuff can I pack into this amount of space. It kind of blows your mind when you think about some things that scientists talk to us about, like origins. I know that for many of us, we're creationists. We believe that God created the heavens and the earth. Some others say that there's at least an intelligent designer. And there are others that believe that it was all spontaneous. There was no plan. There was no creator. But they offer this suggestion that at one time back in history, there was what is known as the Big Bang, right? Now, what is the theory about the Big Bang? Where was all the stuff that resulted in everything we have? Okay? The idea being that all that we see as not anti, but positive matter, all the stuff that we see as positive matter was compressed into a very, very small volume. Now, depending on who you talk to, the theorist you speak with or listen to, the size of that volume is very, very small. So let me pick something that's many, many, many times bigger than they think. Again, let me use a snowball's worth. because this is many, many, many times bigger than the space that they believe, that these theorists hypothesize, that all the matter of the known universe existed in a volume smaller than a snowball. Which means this whole planet, all the planets, all the celestial bodies, all the stars, all the matter in all those places was packed so tightly that it fit within a space smaller than a snowball. So if you start to think about how many protons, neutrons, and electrons that exist everywhere that we know, and taking all of that and putting into a giant press and pressing it down into the size less than a snowball. It would be very, very dense, wouldn't it? If we were thinking about weight, it would be almost an incomprehensible amount of weight in a very small volume. It's almost an incomprehensible amount of matter, protons, electrons, and neutrons, squeezed into a very small volume. And as you see the relationship here, the inverse relationship, as volume gets very, very small, density for the same amount of mass gets very, very large. And so density, I want you to think about density as the relationship between how much stuff I have in a certain amount of space. We talk about the different phases of matter. We have solids. And I keep saying, okay, if we take the same amount of stuff, when we talked about water, for example, we have a liquid water. And then as we change the phase from liquid to solid, when we freeze it, we said water is unique in that as it moves from liquid to solid, it actually expands. It's the same amount of material taking up a greater volume. The same mass of material, so this doesn't change, but the volume gets greater. And as the volume gets greater, the density then has to get smaller. Okay? So make sure you understand questions when you talk about density. Are you keeping the amount of material the same, or are you keeping the volume of the material the same? Okay? Because if I were to say, okay, I've got frozen water, and I cut out a certain volume, then I take that material and I melt it, what's going to happen to the volume? See, it's kind of the same question backwards, or different aspects of the same question. So density is the amount of material or the amount of matter, the mass of an object, divided by its volume. I think we did this question a while ago, but on page 219, this isn't in second edition, so the second edition, just follow along with the discussion. Third edition, we are on page 219 on example 6.1. It says that a gold miner has found a nugget of pure gold, and he measures its dimensions and then calculates its volume. Remember, volume is a three-dimensional concept. You got height, width, and depth. So you're looking at shapes like cubes, or whatever the shape is, it has a certain amount of volume. Now, if I wanted to find out the volume, let's say I wanted to find out the volume of this eraser, what are a couple ways I could do that? What's one way to figure out the volume of this object? Right, that's the second method. And we'll do that one in just a minute. The first method, the more obvious method is, at least for many people, is to measure it. I'll measure this length by this length by the depth. So my height times my width times my depth is going to give me a volume. Let's say our units here were centimeters. Then my units for my volume would be cubic centimeters. It's a volume, right? I can convert cubic centimeters to liters. Okay, to liters, and that's the point that Blake was making. I could also then take a volume, take one of our large graduated cylinders, fill it to a certain amount with liquid, take this eraser, submerge it in the liquid, and see how much the volume goes up. I'm going to draw a beaker rather than a graduated cylinder. So I've got a certain amount of liquid in there, and it's going to read at a certain level. I then could take the eraser, submerge it, and when I submerge it, the level is going to rise, and I would read that level, and the difference between the two is the volume of the object that I placed in the liquid. See? It's going to change because a certain amount of the liquid is going to be displaced when I fill that volume with this solid. So it's at the lower level. I bring this inside, and when this eraser is inside, it's going to move the volume up. And the difference between the two volumes, the volume delta, the change in volume there, is equal to the volume of the eraser. So I can find out the volume of the eraser by either doing the measurements or by submersing it and finding out the change in the volume level of the liquid to compute the volume. Then, to find the density of the eraser, I need the mass divided by the volume. Well, I've computed the volume in one of these two ways. I need to find out the mass. And I just use one of my triple beam balances over there, which is, we're going to go ahead and weigh it on the triple beam balance and figure out how many grams of matter are contained within this solid eraser. That's going to give me my mass number. So when I have the mass, I divide that by the volume, and that's going to give me my density. That's going to tell me for any given space, any given part, any given volume on here, how much matter am I going to find in that place. Now that's assuming, of course, that this is consistent. We know there's felt and there's styrofoam, and it's, it's different volumes even within the solid. But if it was a homogeneous solid, this would tell us how much matter I should find in any given volume, any given piece of this, and also as the whole. Okay. So he says a gold miner found the nugget. He computes to find out that the volume is, in this case, was it 1.125? Yeah, 0.125 liters. The volume is 0.125 liters. And that the density of the gold is 19.3 grams per milliliter. Calculate the mass of the miner's nugget. Okay. So again, in this rho equals mass divided by volume, mass per volume, the rho is 19.3 grams per milliliter, and my volume is 0.125 liters. It says, what is the mass? So this is my unknown, and I would just solve for that unknown. 19.3 grams for every 1 milliliter. You see that? Have we written it this way? 19.3 grams for every 1 milliliter times, because my denominator here comes up to the numerator, times 0.125 liters equals what I'm looking for. But I have an issue here, don't I? What's the issue with this setup? My units. Good. The units here, I've got milliliters and liters. Do they cancel each other out? They don't, so I need to convert. I would hope to have milliliters on the top, right? So let me move this out one more time. 0.125 liters. I need something here that relates milliliters to liters, because that'll get rid of my units milliliters to milliliters. It'll also get rid of liters to liters. So I need something that relates milliliters and liters. What is it? How many milliliters are in a liter, or how many liters are in a milliliter? 1,000 milliliters is in 1 liter. Now I can do the math. Yes, ma'am. Mm-hmm. So then I do this math. 19.3 times 1,000 times 0.125. That math, that many grams. Because rho equals mass per volume. If I have 2, I can solve for the third. The answer then comes out to be 2,412.5 grams. Which is a little bit more than, it's 2.4 kilograms, and a kilogram is what, 2.2 pounds? So it's almost 4.5 pounds of gold. Is that right? 2.4 kilograms. That's a serious piece of gold. All right. Good news. We're on to a new subject, the part of this chapter that is actually more real chemistry. We're going to start talking about chemical equations. This morning in homeroom, Lexi, remember what you said? I was comparing your excitement this morning to an event that happened in your life. And I said, that's the way I feel when you learn how to balance equations. She was so excited this morning about something that happened. And I said, that's how I feel when you all will learn how to balance chemical equations. So let's go ahead and start looking at balancing the chemical equations. We're on page 222 in third edition. That relates to 116 in second. And the author starts with a couple things that really are repeats by now. You've heard these ideas and you've heard me say these things before, but that's part of the nature of chemistry, and part of the nature of many things is you say certain things and you assert certain things and you use it, and later on you learn the things you've asserted. In this section here, they talk about reactants. Reactants combine to produce products. And we've been using this kind of nomenclature up to this point. You've seen me write on the board, for example, A plus B reacts to produce C. Or C produces A plus B in a decomposition reaction. Okay, we've talked about those things in the past. So we've got reactants and products. And we start with reactants, and we move from reactants to products. The example they use in the book of this is, for example, if we have carbon and oxygen. Now, elemental carbon is just the symbol C, and elemental oxygen is O, but oxygen is a homonuclear diatomic, right? So we're not going to find oxygen just single oxygens together but not connected in some way. And we talked about this as homonuclear diatomics, that they form a molecule of oxygen. So carbon, one carbon atom, and one oxygen molecule, right? This isn't an oxygen atom, this is an oxygen molecule because it's two atoms connected together, react to produce a CO2 molecule. The reactant carbon, elemental carbon, and a molecule of oxygen react to produce a product which is carbon dioxide. Now, we're going to take some of what we saw in molecular geometry and talk about what's really happening here. What's actually taking place. In figure 6.3 on 223 kind of goes through this idea that you start with a carbon atom and you have an oxygen molecule. You've got an oxygen and an oxygen bound together with a double bond. It's a covalent bond between them. Okay? So you have a single element and you have a molecule made up of two atoms in relationship with a double bond. In order for me to go and produce carbon dioxide, the carbon is going to set itself up in the center, and rather than black dots, I'm going to use just circles with the abbreviation in the middle. You got a carbon, and you're going to end up with double bonded to an oxygen, double bonded to an oxygen. Notice over here, let me go ahead and keep the same symbology. So we have a carbon atom and yes, I know it looks like glasses. Because I can do that, right? No, I'm not going to go there. That gets too much into dad humor. But I've got a carbon atom and an oxygen molecule. They're going to react to produce this. What do you notice about the geometry here? What do you notice about the makeup of this product? I haven't just simply taken a carbon and attached it to an oxygen, have I? It doesn't look something like this. Right? I haven't just taken this and the plus sign is just kind of like glue. I'm going to stick them together. What's actually happened here? Well, to go from this carbon and oxygen molecule to a carbon dioxide molecule, there's an intermediate step where the carbon and the two oxygens, what actually has to happen is the carbon stays the same, but an oxygen and the oxygens have to separate. There's a breaking of the bond that takes place there. So once you have this break, then we can reconstitute it in that form. Think of it this way. This carbon actually comes in, muscles its way in between in this bond. And so we're breaking a double bond and then forming two double bonds. And all of that takes place symbolized by that arrow, the reaction. The reaction is either going to be spontaneous or it's going to take energy to cause it to happen. Okay? So it's either going to just happen on its own, or we're going to have to go through, and I'm kicking the toes of the front row, because you all have sharing a common condition. Okay. I know I'm not that exciting, but I used to know how to juggle and I forgot. Here we go. So you've got this bond that has to break and these two bonds that have to form, and they all take place in this symbol in time known as the reaction. The reactants produce the products. The reactants react to form these products. Go ahead and add a little bit more information to this. We're looking back at our first equation right here. Carbon plus oxygen molecule produces carbon dioxide molecule. And table 6.1 gives us our phase symbols. We can add a little bit more to this to say that carbon in its solid form and oxygen in its gaseous form react to produce carbon dioxide that is in the gaseous form. So, a solid piece of carbon. Think of carbon. When you think of carbon, think of coal or charcoal. It's mostly carbon. If I put a chunk of coal on the table over there and I left it in the air where there's oxygen, would I expect that the coal would slowly melt away and disappear as it mixed with the oxygen in the air and became CO2 gas? Do you think that happens? No. This is not a spontaneous reaction. This is not something where the two elements say, hey, we're together, boom, let's do it. It's like, we'll do it, but you got to put a little energy into us to make us want to do it. Now, how do you think you can produce carbon dioxide from coal? You burn it, right? As a matter of fact, it's called oxidation. You oxidize it. You give it some energy. The energy takes the fuel and mixes it with oxygen to produce products. And one of those products being carbon dioxide. The other one being ash, and the other one being water vapor. We'll get into those standard reactions later on. But for right now, the solid carbon and the gaseous oxygen molecule react to produce gaseous carbon dioxide. And they react to produce, that reaction requires energy. Usually we see that in the form of burning it. We're adding energy to it, it starts to burn, and through the energy of combustion, it produces carbon dioxide. In 6.1, it has 3 or 4 different symbols. They represent the different phases we've talked about. Obviously, solid, liquid, gaseous, and the fourth one, aqueous. Aqueous means in water. So if it was aqueous carbon, it would be carbon mixed in water. That's what aqueous means. It's not possible to have H2O aqueous. That's redundant, right? Water in water. Duh. Water is always aqueous. But for everything else, it could be in water. For example, if I go over and I've got aqueous sodium, that means I've put sodium in water and mixed it up. Probably had a pretty good explosion when I did that, but aqueous sodium means sodium in water. It's from solid, liquid, and gas. Remember, when it's aqueous, that just means water molecules have come in and placed themselves between the atoms or molecules of whatever is aqueous. In the case of sugar, we talked about that yesterday. When you dissolve sugar in water, it's sugar aqueous. You know, that means that water has come in and every single molecule of sugar now is surrounded by water. And since all the sugars aren't next to each other, we see the water, not observe it as a solid chunk of sugar. All right. On page 224, we're going to talk about burning methane. Erase these. I believe the book presents two different ways to think about it, one that's inaccurate and one that is accurate. Yeah, figure 6.4 shows the wrong way of looking at it, so figure 6.5 shows a more appropriate way of considering it. They show CH4, that's methane. It's, what kind of a shape is that? Those of you that have 3rd edition, 6.4. Tetrahedral, okay? So we've got carbon. We'll present it here as tetrahedral of methane and oxygen. And oxygen is a linear double bond. The CH4 and O2, okay? One way, which is the incorrect way of doing it, I think anytime they show you the wrong way, they know it's a common misunderstanding, right? Like, I try not to show you the wrong way to do stuff and then go, oh, just kidding, don't do it that way. Okay? So it must mean that this would be maybe the more natural way of thinking about it, or the way that a lot of people try to think about it. And there's a reason to show you the right way later, after you look at the wrong way. But it says here, let's start with these two things. We've got methane and oxygen. Now, one way would be to say, okay, we're just going to completely break this all down into pieces, and that's going to give us a carbon and Blake and Sydney, be quiet. Now you're on tape forever. Okay, you got a carbon and 4 hydrogens and 2 oxygens, right? If you were to break all the bonds and just have the elements, this is what you would have. Now, if you know that you're going to produce carbon dioxide, so you've got methane, CH4 plus O2 produces carbon dioxide, yep, CO2, and something else. Just leave that something else there. If I go and start trying to produce my product from these building blocks of 1 carbon, 4 hydrogens, and 2 oxygens, I know that I need CO2. Well, let me take the carbon here. That counts for that one. And I've got the building blocks of 2 oxygens, right? So I could put my 2 oxygens like that because I know it's going to be a linear molecule like this. So there's my 2 oxygens, boom. But now I'm left over with 4 hydrogens. So if I did it the wrong way, thinking about it this way, I would have CH4 plus O2 produces CO2. I've got my CO2, but now I've got 4 hydrogens I need to deal with. You might put it like this, 4 H2s, or 2 H2s. I get leftover hydrogen. But that's not actually what happens. What we have, thinking about it in the correct way, is we actually produce not 2 hydrogen molecules, but we're going to produce 2 water molecules. So how does that happen? Well, rather than having 1 methane molecule and 1 oxygen, let's up the building blocks we start with. Let's add another oxygen here. Okay? So now what I have is a methane and 2 oxygen molecules. When I have 2 oxygen molecules, if I break it all down, I've got 1 carbon, 4 hydrogens, and 4 oxygen molecules. Or excuse me, 4 oxygen atoms. Now when I go through and start to construct my product, I have a carbon, 2 oxygens, so I'm going to use 2 of those blocks to do the oxygens, and what do I have left over? 4 hydrogens and 2 oxygens. So if I know I want to form H2Os, this is my carbon dioxide, and now I have H2O. Let me see, there's 2 and there's 1. What do I have left over? I have 2 H's and an O left over. So I can actually form 2 water molecules. And that's what we actually find out. 1 methane and 2 oxygens. This is 1 oxygen molecule. We don't want 1, we need 2 of them, right? 1 methane, which is 1 carbon and 4 hydrogens, and 2 oxygen molecules, which is actually 4 oxygen atoms, correct? You see that? We need to refresh our memories on subscripts, coefficients, and superscripts. Do you see here that there's 1 carbon, 4 hydrogens, and 4 oxygens? Then over here we've got 1 carbon, 2 oxygens, and 4 hydrogens, and 2 oxygens. Well, this is what we're going to do as we balance to find out what, or look at these different reactions to find out if they're balanced or not. I'm going to suggest to you that this is a balanced equation. What does a balanced equation mean? It means it follows the law of conservation of matter, conservation of mass. That we can't create something out of nothing, only God does that. And we can't take something and make it into nothing, only God does that. All we do is rearrange the pieces. Each atom is a Lego. We can't make the Legos, but we can build different things out of the Legos. Okay? And what we're doing here is making sure that we start with a certain amount of Legos, and we build something, and when we're done, we use all the Legos. We can build something else out of it, but we've got to account for all the Legos. We can't throw them away, and we can't add any more. We can just rearrange them. So let's look at this equation right here and find out if it's balanced. If it's balanced, that means we've used up everything we started with. If it's not balanced, it's not correct, and we need to balance it. So the first thing to do is to find out, is it balanced? Looking at this, I'm going to go through and look at every element that's in the product side. What do I see as I go from left to right? The C, right? What is that? Carbon. Good. I got it right. Okay, next one. Hydrogen. Then what do I see? Oxygen. And then what do I see on the reactant side? Anything else? No, that's it. Now, I'm looking at my list here. Let me go to the product side. Go from left to right. What do I see first? Carbon. I got it. Next? Oxygen. Got it. What do I see next? Got it. And then I see already on there. So everything that I started with is somewhere in what I finish with. So the kind of blocks I have, if you think of Legos, and this is a red, blue, and green, when I get to the end, I need to have red, blue, and green. Can't add a color that wasn't there to start with. Can't have extra of anything laying around. Right? I've got to count for every kind. And I've done that by saying carbons, hydrogens, and oxygens are here. Carbons, hydrogens, and oxygens are here. Okay, so at least I know I've got all the same type of blocks on both sides of the equation. Now I'm going to go through and count my building blocks, count my Legos. Stay with me here just for a moment. We're looking at the reactants and the products. How many carbons are over here? Let's go from left to right. Carbons? Okay, 1 carbon. Hydrogens? 4. Oxygens? 4. Am I done? Am I done for the reactants? Yes. Let me go to the product side. We go from here. Carbons, 1. Oxygens, 2. Hydrogens, 4. Am I done? No. Oxygens, how many? 2. All right, look at my answers. 1 and 1. 4 and 4. 4 and 4. It's balanced. See you tomorrow.